John.
Jeez. The screen there. Everyone view the slides?
Yes.
Perfect. All right, everyone. Thank you for coming to today's GeoMPAC seminar, and thanks to Adil for inviting me.
John, I've accidentally muted you.
No
Sorry
problem
about
at
that.
all.
Carry
No
on,
problem
please.
at all. Okay, so as Adil kindly mentioned, I'm John Ryan-Purcell. I'm a PhD student of Stefan Hutzler's in the TCD Foams and Complex Systems group at Trinity College Dublin. Today we're going to talk about the work, as Adil mentioned, that he's contributed to as well, of arrangements of spheres in transverse confinement. So this is work that the group had begun slightly before I started, but which has been developed extensively through my time, the last 3.5 years of my PhD with the group. And this will be kind of a summary of the work we've done up until this point in this topic. So what exactly do we mean by a set of spheres in transverse confinement? And I find it helpful to start on the macro scale in this regard. So this is an at-home experiment done by a previous PhD student of the group, Jens Winkelmann, who finished his PhD just as I was starting. And this is simply a Perspex tube filled with golf balls. And so these hard golf balls are deposited into the tube one at a time, and you form these interesting helical kind of structures and packings of these golf balls within this cylindrical confinement. Now, I mentioned Jens, and to give him some free publicity here, and an excellent source of reading, if you are interested in pursuing this topic further, him and Ho-Kei Chan have just published a book on this topic, the columnar structures of spheres, which is well worth the read and available through Taylor and Francis online publishing, I believe. So yes, we can form these 3D packings and structures by depositing these spheres into cylinders. However, an alternative method for constructing these structures was proposed in a paper by Lee, which is to have these spheres which are less dense than a fluid, suspended within a fluid and contained within this rotating cylinder. So instead of the hard boundary walls of the cylinder, like such as the Perspex tube and the and a hard cylinder, you have this transverse cylindrically symmetric confining potential, which is approximately harmonic. And so you assemble these similar kinds of structures, but you have slightly more freedom in how these structures are assembled. And so it was this kind of, these rotational columnar structures was kind of where the beginning of my work starts. Because clearly to assemble these structures, you need a larger number of spheres. So the spheres times their diameter must be much greater than the length of the tube you're using. But what if we consider a simpler system, for example? What if we consider a single line of spheres contain a potential like this? And where we end up is kind of in the beginning with these 1D colloidal chains. So you can imagine a colloidal fluid, for example, where you have some sort of particles. If you increase the concentration, or in the example here of the Fe3O4 molecules, if you hold them within a magnetic field, again, this transverse confining potential, you form these long linear chains of molecules or of colloids. And then it is possible by increasing the magnetic field you can compress these systems down. You form these so-called zipper structures that we look at. And we're going to talk in this kind of in more detail later. But kind of the through line of this talk is this movement from the 1D colloidal chain to the 3D packing structures that we see in these in the Lee paper and in Jens and Ho-Kei's working book. So just to give a quick overview of what's going to happen. First, we're going to look at how we simulate and characterize these hard sphere 1D colloidal chains. So this is the simple, basically the line of particles. I'm going to give a brief nod to the continuum model, which Stefan and I have worked on throughout my PhD, which is a differential equation which describes the displacement profiles of these buckled lines, in particular for hard spheres. And then we're going to move on to talking about these chains with soft spheres, implementing a analytic way of describing bubble shapes called the Morse-Witten model. And then finally, we're going to talk about the transition of these from these chains of spheres to these columnar packings, as shown on the first slide. All right, so starting with a simple experimental system that was put together by a member of our group, Ali Oranejad. Here is a picture of a set of hard ball bearings sitting at the bottom of a cylindrical tube. So while this potential isn't exactly harmonic, it provides a good approximation and a good illustrative example of the kind of profiles that we're looking at. So at the end of these tubes are two hard walls, which are pistons, so the distance between the two pistons can be varied. And as these pistons are moved closer and closer together, we form this buckling profile. Now we characterize this buckling profile by looking at the angle the line between sphere centers makes with the horizontal. And so in the second image, you can see the image of this buckling profile. Of note, there's some, it demonstrates the kind of localization of this buckling. We have a sort of narrow peak with these kind of inflection points in the tails, and it's relatively symmetric, which we'll talk about in more detail in a moment. So in order to look at these buckled structures more closely, right before I joined, there was a kind of iterative approach developed. So we'll break down what's going on in this slide. So for these buckled structures, each sphere experiences a restoring force, moving it back towards the central axis of the potential, indicated by capital F, and also experiences compressive forces exerted on it by the neighboring spheres. Of note, when this system is horizontal and flat, these compressive forces, the horizontal component is purely due to whatever force the entire system is exerting on the walls at the end. This given by the script G. An important quantities to note here are obviously the compression, which is simply the difference in length between the natural length of the chain, so n times d, n being the number of spheres and d being their diameter, minus the current length of the chain, L. You can also calculate this by summing over the angles for each sphere from the cosines of the angles of these spheres, if the sphere diameter is 1. Based on this force balance and the geometric relationship of this structure, an iterative method was developed, which can be used to, using a method like the shooting method, can be used to calculate buckled structures of this kind. And examples of this, which are done by Adil, thank you very much, Adil, where for 5 spheres contained within this potential, and we used the shooting method to find structures that are in mechanical equilibrium. So as you can see, there are kind of a rich variety of structures for given values of compression, but the ones we're particularly interested in at the moment, and the ones we'll be looking at, are these kind of what we would like to consider the ground state structures, so that they are the lowest energy structures of this system, which are these S structures here, these symmetric structures under compression. So noting that for these symmetric structures, that the displacements away from the central line are quite small, and these profiles are quite regular, that they're pretty well behaved for these symmetric structures. The question was, well, could you create some sort of underlying continuum theory at which you would sample at the correct value of the sphere numbers in order to create to build up these discrete profiles. So this continuum theory would describe buckle structures of this symmetric kind for any value of n. And so the reason I showed those iterative equations earlier is that we worked backwards through them and realized that, well, using a kind of a reversal of a discrete version of the central difference method for second derivatives, you can construct a second derivative equation where now instead of the angles of the displacement profile being given by the sphere index n, we make them continuous. We turn it into a continuous variable u. We therefore develop this continuous model, which results in the second order differential equation in phi of u, where phi is tan of the angles. So you can consider this like the slope of those center lines of those spheres. And in order then to find that these profiles that we saw earlier, we simply find solutions that satisfy the boundary conditions, where that phi of 0 is phi of n is 0. And then the compression quantity that we talked about earlier is now, instead of a sum over the angles, we make it an integral over those angles. And so the solutions that you see in the image here are certainly match the profiles from experiment and the iterative simulations in character. You originally have these, as you compress more and more, you get these narrower and narrower peaks with these inflection points and exponential tails. Perfect. So we also found it interesting to add another dimension to this problem, which is this idea of tilt. So in order to break the symmetry along the central axis of the system, you can add a longitudinal force which acts along that direction. And so the implementation of that is simply that the compressive force acting along the spheres now picks up this tau times u term. And this tau times u term represents the weight of spheres above a sphere in the chain, which then breaks the symmetry in the system. We now see that these buckling peaks move towards the bottom wall as tau is increased. And we're going to talk about that in more detail as we look at the analytic solutions. So unfortunately, this equation as it stands is not easily or not solvable analytically. The solutions I showed you earlier were numerical solutions for this problem. However, there are certainly cases in which we can reduce this equation and solve it analytically, and that's what I'd like to talk about next. So here's a quick table that will kind of summarize what the overview, the next bit of the talk is about, which is that we have kind of three different scenarios in which we found analytic solutions for this differential equation. So remember, starting with the full equation with tilt, if we consider tilt equals 0, we have a reduced version of the equation that results in Jacobi functions, which I'll talk about in a moment, as seen in the first part. For small tilts and small compressions, we find a version of the area equation, which is shown in the second graph on the right. And then finally, for where this compressive force of the wall goes to 0, we find Whittaker functions and solutions, as shown in the third graph on the right here. All right, so talking briefly about the Jacobi equation and what it shows us, well, if we have the case where tilt equals 0, the Jacobi equation, the full equation reduces down to a rescaled version of the Jacobi equation. Here we introduce this new way of writing the compressive force of the wall, kappa squared is equal to 1 over g naught minus 4, because it gives us an insight into how the number of spheres in a system affects the characterization of the buckling. So the solutions for this Jacobi equation analytically are a special Jacobi Cn functions. But the only thing you need to know about those now is that they go with, they look approximately like cosine of u for kappa squared less than 0, and they look approximately like the section of u for kappa squared greater than 0. The reason this is interesting is because these single peak symmetric solutions for smaller values of n don't exist for different values of n. So for example, in the graph now on the right here, we see that the n equals 10 system has a large region of compressions where the single peak solution has kappa squared is less than 0. So this is a representation of remember, this is a representation of the compressive force exerted by the wall. But as we move towards the infinite system, this region disappears. And so the reason I want to bring this up is that for small values of n, you get these cosine-like solutions where they don't have these inflection points here. But as we move to larger and larger n systems, that region gets smaller and smaller until for infinitely large systems, as soon as you begin to buckle, you get these inflection points and you have this kind of highly localized buckling that we saw in the first few profiles. Moving on to the second example, the second analytic regime. There we go, which is where we have the small compression limit again, but non-zero tilt this time. We have a linearization of our original equation, which is a rescaled version of the area equation. So solutions of the area equation are given by area A and area B solutions, or linear combinations of area A and area B functions. And this allows us to build up a nice picture of what the solutions look like as they evolve with tilt. So on the left-hand side, you can see that we start with an initial structure, which could also be described by the Jacobi solutions. And if we fix the value of compression, but increase tilt, the area solutions give us a good estimate, a good representation of how these structures evolve as we tilt the system. Then moving to the graph on the right, another interesting prediction that the area solutions can give us is the position of the peak at compression equals 0. So if we start with a linear chain and begin to compress, well, where does the peak form as a function of tilt? And the area solutions give a prediction here. So with the red line is the area solution, and the blue dashed line are the numerical solutions to the full equation. And so they show us where this buckling sort of begins, or where this localization is as tilt is increased. Then finally, for the case of G equals 0, so this is where the compressive force exerted by the top wall goes to 0, we notice that the equation reduces to a version of the Whittaker equation. The solution I show you here includes the special Whittaker function m, but again, it's not so important to understand the details of that. I just wanted to point out a few notes about it, which is that the compression of this solution is scalable because the derivative at phi prime of 0 is a free parameter in this result. So the Whittaker equation holds for any value of compression there. But more importantly, because of the rescaling of the variables, the solution relates periodicity to a choice of tilt in this case. So to define the Whittaker solution defines an n and t pair. So what is the meaning of, so if we calculate, say, the solution for n equals 10, we get a specific value of t. Well, what's the meaning of that solution? Well, eventually, at some point when you tilt one of these systems, they are going to detach from the top wall. The top sphere will move away from the top wall as the weight of the spheres compress the system below it. And so these Whittaker solutions, how they relate the value of n to the value of t, they correspond to the critical value of tilt for that given compression, for that compression TC. So on the left-hand side, we see how the compressive force exerted by the top wall decreases as a function of tilt, and the Whittaker prediction makes an estimate for what value of tilt that will occur. So on the right-hand side, then we have a comparison with the discrete simulation of these profiles with tilt in them. And we can see that the Whittaker solution really does make a good job of estimating these critical values of tilt. To kind of sum all of this up and talk about the regions where all of these relate to one another. So we have here now a plot of compression versus tilt. These buccal structures all exist to the left of the blue line. And so, of course, the Jacobi theory is all for tilt equals 0, and so exists primarily on the y-axis. The Airy theory for small compression and small tilt exists in a region around the origin. And remember, this Whittaker point gives us an estimate of where this detachment occurs at compression equals 0. And so then this blue line defines the point where to maintain these single peak symmetric solutions, you would, beyond this point, you would need an extensive force at the top wall rather than a compressive force. Perfect. So then all of these buckled symmetric structures that we looked at exist to the left of this line in compression and tilt. Hopefully this impresses you on the fact that even such a simple system has a relation to quite a lot of deep mathematics here. For example, Jacobi theory, the Jacobi equations or the Jacobi elliptic functions are used in describing the motion of nonlinear pendulums. And like the Airy equations here are used in everything from quantum mechanics to probability theory to optics. So we're really covering quite a wide range of mathematics here. But of course, everything I've talked about so far is really only for the hard sphere colloidal chain and really only for the point, but for points below where this transition to the 3D packings that we saw earlier came up. But to talk about that in more detail, I'd like to first move on to the soft spheres. Perfect. So moving on to these soft spheres, where now these particles are no longer hard and undeformable, but rather as you apply force, these particles change shape. These appear in biological systems. On the left-hand side, we have the development of these notochord, which is kind of like the developing spine in embryos and such of a zebrafish. So these are, in the top picture, you see these vacuolated cells. And as these cells grow, they take in liquid and then they form these packings, not unlike what we see here. On the right-hand side, we kind of have a macro version of this system, which again, Ali in our group is responsible for doing, were these hydrogel spheres. So these hydrogel spheres, again, like the zebrafish cells, over time, they absorb in liquid and grow within the system. And eventually, as the number of spheres times their diameter, natural diameter, grows longer than the length of the tube, we see this buckled formation emerging again. So stripping it right down to look at the soft spheres in the kind of simplest possible system, we have a quick look at bubbles held between two plates, again, in this confining potential under compression. So if you now with the soft system, with a one bubble system, you can see as you compress the system together, these bubbles, in order to conserve their volume, squeeze out. But the interesting thing now, unlike the hard spheres, which begin to buckle under infinitesimal compression, there is some sort of critical value of compression at which these structures begin to buckle. At some point, the bubbles just squeeze together, but eventually it's more favorable for them to buckle by moving outwards. And so our aim is to describe the change in width of this system as a function of compression and how this changes with our measure of softness. And so our measure of softness here is going to be the bond number, kind of number which characterizes the competing forces of, say, buoyancy and surface tension. And in general, you can think of the easiest way to think about it is that the lower bond number refers to harder particles. So as bond number goes to 0, we have the kind of the hard sphere limit that we were talking about here. So bond number going to 0 would be surface tension going to infinity, or say extremely small bubbles. Or one of the example I like to use is you see the bubbles that street performers use, the massive ones made with between two strings. They deform and they're not very spherical at all, whereas the bubbles you might blow from a smaller, these small kind of party toy ones are always very highly spherical. So they don't deform much under an applied force. So describing the shape of these bubbles analytically is kind of a difficult problem. So what we are going to use here is an application of the Morse-Witten model, because in particular, of interest to us is, like I said, this change of width is under applied compression, which most bubble models, which are such as like the soft sphere model, which models bubble interactions as allowing overlaps, but they don't capture the change in shape of the bubble under these applied forces. So we thought this was a good example, a good time to use the Morse-Witten model, which simply describes the surface of the model, the surface of a bubble as this R of theta function. This deformation is applied using a point force. Okay, this point force has a logarithmic term in it, which explains the deviation right at the point where the force is applied. However, a capping procedure is used here to maintain the physicality of the bubble shape. So this is a little bit softer than Hooke's law, but this bubble is strictly based on a linearized version of the Laplace-Young equation, but also takes into account the fact that the volume is conserved under this applied force. And this is the important part. As you squeeze these Morse-Witten bubbles, they extend correctly in the right direction. Hopefully the next slide will make this a bit clearer, which is where we are looking at this aspect ratio. So kind of the original problem where this model was used for, where we have a single bubble held under a plate by buoyancy. And if we compare this aspect ratio as a function of bond number, the Morse-Witten model compares very favorably to, say, experimental data, but also to exact solutions of the Laplace-Young equation for this situation, and also to surface evolver software used to measure to calculate these bubble shapes. The advantages that Morse-Witten has here is that Morse-Witten is exact in the low bond number limit, so we're in the case where the forces are very small, which gives an advantage over surface evolver, which can struggle in that area. So considering then again this 1 and 2 bubble system, the Morse-Witten model, with no free parameter, simply using the bond number as this measure of softness, can make a pretty good prediction for the change in width as a function of this compression, this compressive strain here. So compressive strain is just this compression divided by the number of bubbles in the system. So on the left-hand side, we see this change in width is pretty accurate, but it also provides a good prediction for this buckling point. We have no free, this should say, Morse-Witten prediction, there's no free parameter in the initial increase of the width. And so we see that Morse-Witten is a pretty good example of, a pretty good predictor of the change in width of these structures as they are compressed, and also gives a good predictor for the point at which these structures begin to buckle. But of course, this kind of analysis only will work as far as, again, these 1D colloidal chains. To kind of move on to these 3D packings, we need to kind of understand how we must apply this Morse-Witten model, or how these structures do evolve into these 3D packings. So here are some images prepared by a member of our group, Ali Iranijad. So Ali's tube, and this is an example of the lathe experiment again, where we have spheres of a high density surrounded by fluid. These are the tube is rotated extremely quickly, and the spheres are pushed to the center. Ali's tube is of fixed length, so in order to increase the compression, he increases the number of spheres within the tube. And you can see as we move from 13 to 14, we get this buccal structure, but eventually we find the formation of this zipper structure. And we find from simulation and mostly from experiment that this zipper structure remains mostly in one plane as you increase the bubbles, the number of bubbles or the number of particles here, or in our case, increase the compression. But eventually, one of these zips will twist out of plane with the rest of the structure. And this is kind of the point at which these 1D structures form these 2D structures, but then these 2D structures become these 3D packings that we saw back at the start. So then we see again here this kind of this now 3D packing, now this structure which is buckled out of the plane. And as we increase the compression, we eventually return to the structures that we saw earlier. To move then on to soft sphere simulations done by Adil himself, here we see this movement from the buckled structure to this zipper structure, how this zipper structure then grows and then begins to twist into this 3D structure. And so Adil prepared a nice video of this this process, which I hope everyone can see. I am not able to make it larger or full screen. I hope it is large enough for people. So then we see this zipper structure form as this structure is under compression. Eventually then we again see the development of the this twisting of the zip at the lower end of the structure.
John, it doesn't seem to run. We can't see it moving.
You can't see any movement there?
I think I can.
Maybe it's the playback speed is too low. All right. Okay, I will ask Adil to share out the YouTube link at the end of the talk, if or I'll post it in the chat. Actually, is the easiest thing to do. Once I'm done there, and then hopefully you can see this evolution as it moves on. Of course, maybe you're tempted to say that this is a result of interactions with the boundary or something. So my goal then was to use our Morse-Witten calculations to see if we could observe the same thing. So starting with the linear chain, can we see the development of the zip and then the movement to the this 3D buckled structure? And so I implemented some calculations on Morse-Witten, and the results are rendered in Blender here. So under compression, and also I used 4 spheres, unlike the 1, 2, and 3 sphere system, because this 4 sphere system is the first time you will see the development of these 3D buckled structures. Everything else will obviously be remaining in one plane. So we start with the linear chain. The red dashed line represents the central axis of the confining potential. We move to the buckled structure. And then finally, as the system is compressed further, I remind you that these are all Morse-Witten bubbles, so they are soft. You can compress this linear chain further before buckling. We see this mostly in plane doublet, where nearest neighbours contact, or the beginning of the zipper. And then finally, these structures twist around, and we get this fully 3D packing here. A kind of representation of that development that we saw in the experimental work and Adil's simulations. So I still have a bit more time, but I am coming to the end of this. So just kind of to make a note that we've kind of come full circle in this regard. Now we've looked through these colloidal chains, starting in these 1D structures that buckle that were so well described by the continuum model, looked at how these developed into this zipper structure, and then finally returning to these 3D rotational structures that you can find in Jens and Hoke's book. So a quick summary then, and I decided to include in this summary some perhaps potential discussion points for the talk afterwards. So we talked about this buckled chain problem, and we implemented this continuum model for it. But one of the problems with it is that it obviously doesn't quite go far enough, right? The analytic results only go as far as where next nearest neighbor contacts form. And it's really beyond that point that is of interest to us now, which is where this 2D zipper structure emerges, and then these 3D structures develop. so is there a possibility of developing another approach which could describe that kind of analytically? Another note here is that all of these systems are monodisperse with isotropic particles. In particular, for the biological examples like the zebrafish and stuff, what's of interest to the biologists and stuff, there are packings with non-isotropic particles, such as ellipsoids. And even in the case of where it's applied to, say, nanophotonics and stuff, these colloidal chains are of interest where these particles have some sort of magnetic moment, which also helps them arrange and such. And then finally, the last point is we saw how the implementation of Morse-Witten works for describing these 1D colloidal chains, but also these movements into these 3D spherical columnar structures. But could we extend this to the simulation of, say, bulk foams in the wet limit, where we have, again, these kind of objects which are well described by Morse-Witten, but have significantly more contacts than they would have in these columnar structures. And then, as a kind of nice note, here's an image produced by a summer student who worked with us last year using the Morse-Witten model, rendered in Blender, where we can see these soft particles squished by the weight of the structures above them. And so I'd like to thank my supervisor, obviously, Professor Stefan Hutzler, Professor Dennis Weir, who I think is in the call now, who has been valuable in his in our discussions about this work. Obviously, Adiel for all of the simulations, and also many long Microsoft Teams calls trying to work out where we were going with this. Ali for a huge amount of experimental work, and the rest of the Foams and Complex Systems group who were subjected to the much longer version of this talk yesterday morning. So yes, thank you. If anyone has any questions or anything we'd like to discuss about the work, please let me know.